Hello, welcome to the Scientist Podcast, and this is our second episode where we try to understand the recent science and try to explain things with our esteemed guest. Today we are discussing about the Nobel Prize in Physics 2025, and that went to John Clark, Michel Devoret, and John M. Martinez, and the and they got in the first week of October, the 2025 Nobel Laureate Prize in Physics. And the topic was for the discovery of macroscopic quantum mechanic tunneling and energy quantization in an electric circuit. When I read this, I feel like I'm not smart enough to understand this. So we wanted some expert support. So we have Dr. Vivek Sinha, and who is almost an expert in this field, uh, almost an expert in this field because he has a vast background from doing when if you I'll post their LinkedIn profile and you can see how vast his profile is. So he's trying to he will try in 5 to 10 minutes to explain what are these words, what is quantum mechanics, computers, and why this Nobel Prize is important. So thank you for joining us, Vivek, and the floor is all yours.
Thanks, Avilas. You're very kind. um, See, I'll start with a disclaimer. Two disclaimers. One is like this: my explainer represents my own personal understanding, and in no way represents the position of QTech, where I have learned a lot. And second thing is, no one understands quantum mechanics. Let's put it like that. Or there are very few people in the world that understand quantum mechanics, and this notion has been consistent for a very long time. Personally, I'm quite thrilled that the Nobel Committee recognized this wonderful, this seminal contribution, that too at such a critical time. Many of you, and not like people who are not, well, I think 5 years ago, 10 years ago, people who were into science, who were into physics, chemistry, had heard of quantum mechanics or did some, basic modules in quantum mechanics. And now I on my feed from Yahoo News or Yahoo Stocks, I get news about should you invest in quantum. I hear about Rigetti, I hear about D-Web, and that's phenomenal. That's the progress of entire human civilization. That tells us the kind of knowledge that we are building upon. What's special about this Nobel, and I'll try to give you a very layman's perspective. Um, so when we talked on when quantum mechanics came into being, it was a mix of different approaches. I think one of there were a lot of seminal contributions, but some came from Werner Heisenberg when he explained the uncertainty principle. Also from Schrodinger when he came up with this Schrodinger's equation, and a lot more contributions. But it was always understood. So first thing came that the word quantum or quanta comes with like things are like discrete, like in packets. That's how the whole thing came. And why is because when you're talking about quantum mechanics, you talk about, for example, if energy levels are there, they are discrete. So if I give you a normal spring, you stretch it, it will pull back. If it's a good spring, it will pull. If you compress it, it will push back. It's a little bit like my son when he was a toddler, even now actually. You try to do something and there's always a pullback or a pushback on things. Um, for quantum mechanical systems, it's discrete in the sense that if you can only access certain levels of energy, you don't have a continuous spectrum of like you can keep pulling and it will keep like pushing through. It doesn't work like that. A long term notion before the work of Clark and Martini and Defore came out. The notion was that this is something that is really specific to things of the size of atoms or molecules, like really nanoscopic, microscopic kind of phenomena. What they showed, and what's phenomenal is that they did it something at the level of an electric circuit. Now imagine electric circuit is something that you can build with your hand, that you can see with your eyes, and they showed that actually quantum mechanical phenomena exist at that level as well. So they had these two superconducting electric circuits connected by something called a Josephson junction, and they showed that to put it in a very simple manner, there was a quantum mechanical variable that could go across energy levels that was classically not possible. So they showed, and they actually one of the key papers, if you want to read, and I have it on my screen now. It's a paper in Science, came in 1988, and it says quantum mechanics of a macroscopic variable, the phase difference of a Josephson junction. And I invite you to read this paper. It's beautifully written. It really shows that at something that is at a macro that you can see with your eyes, their quantum mechanical phenomena. It's a carefully crafted system. It's not something that's very random. It's not like a large wall that you build at your home. And because you always get this example of quantum tunneling, that a boy is throwing a ball at the wall, the ball will
Yes.
come back. But
Yeah.
in terms of tunneling, it will essentially pass through the barrier that this wall is. It was not something as random as that. It was carefully crafted, yet they showed the possibility that you can actually have quantum mechanical tunneling, you can have quantum phenomena at something at this size. And that was foundational, that was phenomenal, that opened up many ways, because now, because atoms are difficult we can control atoms. We have this possibility of doing lots of control and lots of physics and chemistry with atoms, but they are difficult. Now it showed the possibility to experiment with quantum physics at something that was microscopic, not really microscopic. So and you can then couple, if you are working with electric circuits, you can interface it with lot of different kinds of electromechanical, mechanical kind of objects. So the possibility to study the effect of quantum mechanics or quantum mechanical phenomena really extended across scale, and they showed that this was possible, and that's why this was a foundational work. Glad that the Nobel Committee recognized it. And my thinking, and it's not my thinking alone, it's many experts also think that this is just the beginning. This is just the very first Nobel that has been given in this field. The work of Nakamura in Japan, their collaborators, but also, for example, Hans Moy in Delft. They were building upon the sort of the sitting on the shoulders of giant, really sitting there and building upon, because they showed that actually, okay, you can do quantum mechanical phenomena on these macroscopic objects. You can also exercise coherent control. That's what Nakamura showed, that you can actually control the states. You can that was the beginning of what you would call as qubit, or the artificial atom, actually, that is made of electrical circuit. That's what they showed, that actually it mimics the behavior of an atom, but it's not really an atom, but it's actually an electrical circuit that is under superconducting temperatures. And that unlocked one of the fundamental qubit technologies called superconducting quantum, the transmon qubits. It's one of them. There are many other variations of this, but it unlocked, and that's like a fundamental. That is a fundamental unit that powers quantum processors of modern day. It's the technology that Google and IBM are among many others are pursuing. Rigetti is pursuing. We are also. I am quite privileged to work with this technology. We have this alien brain like. Refrigerators, dilution refrigerators that go to like 10 millikelvin temperatures. And we have these quantum processors where we have electrical circuits that are carefully etched out, carefully created, that you can see with your screen or with a basic microscope. And that actually works on the principles that were, that were foundational, the foundational principles that came out of this Nobel. And I'm sure there will be many more to come. So that it's personally very special to me. I do not have specific stories to share about the Nobel laureates.
That's
I'm
okay.
too early in this field, but I can see, when I talk to the professors that I currently work with, I can see the joy, and they have all of these stories when they had dinner, when they went to certain specific conferences or events with them, and it really brings pure joy to all of them to see something like this recognized. And this whole technology, uh, it's too early to say which qubit technology is going to sort of be the winning platform, but the foundational work has unlocked the power of quantum computing to us. We are still in the early days, but we are at sort of a inflection point of quantum technology in our society. And when we go beyond that, you will see a new revolution. It can even be bigger than what AI brought to us. So
Oh,
quite excited, and there will be lots of convergence. There will be convergence of AI and quantum. It's already happening. And we are in the, I think these are really exciting times. 2025 is the International Year of Quantum, so it's special. It's
oh,
really
wow.
special to see a Nobel granted in that field, recognized in that field. So yeah, it's exciting times.
No, I think that's an incredible explainer. I still have one question. Sorry,
Sure.
I'm taking lots of time. Uh, why an Indian needs to understand this? And are we surrounded by quantum mechanics? Like, are things that we are using? It
Definitely.
so
Um,
so like why we need to understand it? Like, why? as like if someone is from sociology background, biology
Mhm.
background, or political science background, that if that person, even Mrityunjay, who's like brilliant scientist, but who wants to understand, no, this is important, and this is the reality that we live in. So understanding this and acknowledging this will do always better, will be always better for us. And as an Indian, how much do we need this in India? So if you can just share a few things about that.
I have some perspective on that as well. You see, I, I'll talk from the Indian perspective first. Why everybody should be bothered with quantum mechanics? Quantum mechanical phenomena is all around us. We may not perceive it. Um, you know, when you have communication through glass fiber, because quantum technology is not just about quantum computing. There are a lot of quantum phenomena around us that we currently leverage. It's in our mobile phones, it's in our computers. When we work with electronics, especially when we have, you know, this semiconducting chips that get smaller and smaller, there are a lot of quantum mechanical phenomena that you have to deal with. But specifically talking about quantum computing and quantum technology in the sense that we talk about cryptography, quantum cryptography, or post-quantum cryptography world, about what quantum computing can unlock and what quantum sensors, quantum metrology can unlock. Um, you know, we probably design 20-25% of world semiconductor chips in India. It happens in India.
Oh,
And we don't manufacture any of it. That
okay.
imagine that if you look at the world supply chain, I mean, we always say there's this open markets that operate and, you know, free trading and everything, and that has changed in the lately in the current geopolitical scenario. Things are changing, but if you look at the control of strategic technologies that can create or completely debilitate nations. And India is a growth story. When I say it's a growth story, we have not grown all the way. We have a long way to go. We
Yeah.
need to have very good control of supply chains of critical and technology of strategic importance. Quantum technology, AI, they are all dual use technologies. They can find use in many different ways and they can help you build your nation from ground up. Um, Imagine that we are currently dependent on a lot of the global semiconductor supply chain, and that poses a lot of challenges. Um, you know, all the drones, but also all the key medical technology, all of these are dependent on chips, and if somehow we are cut out of that supply chain, it will create it it will be very bad. And we are
Yeah,
already seeing examples of that.
yeah,
Quantum technology can like, you know, quantum computing, post quantum cryptography, once it realize the nations that control it, the governments that will control it, um, it poses serious risk. It is of like, you know, imagine that you have two state actors, one that has an unhackable network, another that has a quantum computer or quantum technology so powerful enough that it's going to, like, you know, lay all your RSA and other encryptions a joke in matter of seconds. And imagine that you don't have a hand on that technology.
yeah,
Um, so it's important to understand all around it. You don't need to become experts in quantum mechanics, but it's important to understand that quantum technology is there, it's going on, and try to sort of like, you know, channel our skill pool development that we become a part of the quantum success story. We build manufacturing hubs, we acquire key parts of technology, we acquire key partnerships with friendly nations, and like, you know, do a lot of capacity development, do a lot of fundamental R&D, so that, you know, and it will be a it can be a big transformative shift. So it's like our chance to, like, okay, we missed the semiconductor bus, no problem. We have this big and we also didn't capitalize a lot on on AI, for example, because it was all powered, it's all powered on semiconductors. You can write all the software that you want, you really need the hardware to, like, you know, run everything on it. So hardware might not give you a lot of ROI immediately, and that's why governments, you know, state sponsored work that comes in, they invest a lot of it so that private investment can get de-risked. We need things like that in India. It's really important that we keep this at top of our focus, not only because it's very important, but also it's a great opportunity for the common Indian.
I think that's a great answer. And thank you for explaining such a complicated thing in a very simple and kind manner. Mrityunjay, any last comments?
I mean, to be honest, like, thank you, Vivek. Really thankful, that you are here and telling us not just about the science behind the quantum and quantum computing, but also the strategic importance, right, of quantum computing, and obviously being very neutral about it, being very, technically sound and right about it. And I think that's really important because, again, like, we're here to also raise a lot of awareness rather than ruffle unnecessary feathers. We don't want to do that. We just want to make sure that people are listening and people know what is important, and you have done it so beautifully, so elegantly. It's really important. So thank you, Vivek, for sharing about quantum computing and today's and this year's Nobel Prize in Physics with us.
Yeah. So
Thank you. There is something that, if I may mention,
sure.
uh, there is something that I'm really passionate about, and it can bring a lot of benefit also to people who want to get started with quantum.
Hmm.
Please feel free to connect with me
Hmm.
uh, on
Oh,
LinkedIn. I hope you'll share my LinkedIn profile,
yeah,
Yeah, yeah,
sure.
we do. Will
but
do.
reach out to me. But also try our free and publicly available Quantum Inspire platform. That
Okay.
is a demonstrator of QTech.
Hmm.
Uh, and it allows you to program real quantum computers, not emulators, real quantum hardware. And
Hmm.
and the QPUs come from the projects that I am directly involved in.
Oh, nice.
I work very closely on the Quantum Inspire platform. So please,
Hmm.
um, now is the opportunity. Go log in, make a free account, and give it a run. Everything is free and completely made for, like, educational purposes. And if you
Hmm.
run into any issues, just reach out to our team. We have a small but very motivated team,
Hmm.
and we love to, like, onboard new talent and help people grow in quantum computing and experience real quantum computing.
Wonderful.
So, thank you so much to have our platform to give this opportunity to people. So that's great. Okay, so we'll let you go now, and
Thank
and
you.
and I hope we'll join again soon. Thank you, and
Definitely.
goodbye.
Thanks, Avilas. Thanks, Mitunjay.
Thank you,
Thank you.
Vivek. Thank
Have
you.
a good